topic is circular motion as simple harmonic motion. Now, in the figure, you see that we have the circular path. The body is at point A initially at rest. When it starts revolving along the circular path, so as the body is circulating, its projection along the diameter is vibrating. Now, these vibrations are not simple vibrations, but it's a special type of motion called simple harmonic motion. So in today's lecture, we will prove that the projection of circular motion executes simple harmonic motion. So consider the body. It starts motion from point A. So as it starts from A and it returns back to A, meanwhile, the projection of this circular motion along the diameter completes one vibration. That is, if the body completes one revolution, its projection completes one vibration. Now it's up to you that whether you take the vibration from A back to A, from B and back to B, or from O back to O, touching both the extremes. So let's decide. Let's consider the body goes from A to C. So as it moves by 90 degrees, meanwhile, when the body moves from A to C by 90 degrees, meanwhile, the projection goes from O to A. And now, when the body goes from C to D by another 90 degrees, that is a total of 180 degrees, the projection comes back to O. Now, when the body goes from B to D by another 90 degrees, the projection goes from O to B. And finally, when the body goes from D to A, completing one revolution, the body comes back to O. The projection comes back to O. So you see that the original motion is circular. The body completes one revolution from A to A. Meanwhile, the projection of this circular motion along the diameter completes one vibration from O, touching both the extremes back to O. So we prove that this projection executes simple harmonic motion. Now you see that when the body goes from A to C, meanwhile the projection goes from A to O or O to A. It's up to you. You take motion from A to O or O to A. Okay? Now let's suppose the body doesn't displace at 90 degrees, but it goes from Now as the body moves from A to B, the projection goes from O to N. Clear? Now join the point P with, draw a perpendicular from point P onto x-axis, and join the point P with the center of the circle. So we have a right angle triangle. Now from this right angle triangle, you can see that base divided by hypotenuse is cos of theta. Now the base is AX and the hypotenuse is AC, and it is equal to cos of theta. Base divided by hypotenuse is equal to cos of theta. Now AX is equal to AX divided by AC is equal to cos of theta. Now by cross multiplication, we get AX is equal to AC cos of theta. Clear? And one thing more, here we will take a negative sign, because when the body circulates from A to C, let's suppose, meanwhile the projection goes from O to A. Clear? And when the body circulates from C to B, the projection goes back. I mean, we already know that acceleration in simple harmonic motion is generally proportional to displacement, but its direction is always opposite to the displacement. Acceleration wholly solely depend करता है displacement पे. अगर displacement ज़्यादा है तो acceleration ज़्यादा पैदा होगी, और अगर displacement कम है तो acceleration कम होगी. But we already have proved that in mass spring system and simple pendulum that acceleration and displacement are oppositely directed. For example, example, let me do it again. If we have a simple pendulum and it is at rest at point O initially, and if we slightly displace it from O to A, so direction of displacement is from mean to extreme. But meanwhile, the direction of acceleration is towards the mean position. मतलब जो भी डिस्प्लेसमेंट की डायरेक्शन होगी, एक्सेलरेशन की डायरेक्शन उसके अपोजिट होगी. अगर आप इसे मेन पोजीशन से बॉडी को मेन पोजीशन से एक्सट्रीम ए की तरफ ले जाएंगे तो एक्सेलरेशन टेंड टू मूव टुवर्ड्स द मीन. एंड इफ यू मूव द बॉडी फ्रॉम O to another extreme which is B, the acceleration is again opposite to displacement. Acceleration always tend to move towards the mean point. So A and X are always oppositely directed. Now, having said that, we already know that centripetal acceleration is V squared divided by R. And what should I put for cos theta? Now, if you look into the figure, as the body circulates, the projection y varies, and the distance covered by varying body from mean position on the other side, on the either side of the mean position, the distance covered by a varying body is called x displacement. तो हम इसे displacement कह सकते हैं. एक बार फिर सुने कि जब बॉडी सर्कुलेट करती है तो meanwhile projection वाइब्रेट करती है, and the distance covered by vibrating body on the either side of the mean position is called x displacement. तो आप इस डिस्टेंस को x कह सकते हैं. मोरओवर हाइपरटेन्यूज को मैंने AC का नाम दिया है, लेकिन मैं इसको RB कह सकता हूँ, which is radius of the circular path. तो अगर ये बेस है, ये हाइपरटेन्यूज है, तो बेस बाय हाइपरटेन्यूज is cos of theta. So we can also put x divided by R, क्योंकि बेस डिवाइड बाय हाइपरटेन्यूज से बनता है cos of theta. तो बेस यहाँ पे x है और हाइपरटेन्यूज यहाँ पे R है. So what do you get? We will get R omega whole square divided by R square into x. R multiplied by R बन गया R square, and we have already studied in angular motion that linear velocity is relative to angular velocity by equation v equal to R omega. So putting R omega for v. Now A is equal to minus R square omega square x divided by R square. R भी square हो जाएगा, omega भी square है, x as it is आएगा and R square as it is. Now similar term will cancel out each other, so we are left with minus omega square x. Now this is the standard equation for SHM. We already know that standard equation for simple harmonic motion क्या है? A is equal to minus omega square x, where omega square is the constant of proportionality. Now, to remove the equality, to convert equality into proportionality, the constant disappears. So, आप equality को proportionality में convert करें. तो जो ही आप equality को proportionality में convert करेंगे, तो constant disappear हो जाएगा, and we are left with minus x. तो साबित हुआ कि सर्कुलर मोशन की जो प्रोजेक्शन है वो सिंपल हार्मोनिक मोशन एग्जीक्यूट करती है. ये रहा हमारा